Welcome back to 8701. So in this lecture, we look at the interaction of W bosons with quarks, so the charged weak interaction of quarks. Let's just make a number of observations. So we observe that the weak interaction respects the lepton generation, meaning that W couples to an electron and an electron neutrino, but not an electron and a muon neutrino. But in the case of the quarks, there is a violation of this. So there is a disrespect of the quark generation when it comes to the interaction with W. So when you investigate these two diagrams here, you find that the W couples to the U quark, to the D quark and the U quark, but it also couples to the S quark and the U quark. All right. In order to encapsulate this, we have to make a correction, and the corrections are typically called cosine theta C and sine theta C. Theta C is a Cabibbo angle, so theta Cabibbo. Turns out this is rather small, 13 degrees, so it is a correction, a small correction. When we studied the partial decay width of the kaon in leptonic decays, over the partial decays to a pion, of a pion in leptonic decays, we found that there is a set of form factors, a form factor for the pion decay and a form factor for the kaon decay. It turns out that the form factors are due to this additional correction. So you find the tangent square of the Cabibbo angle as part of this correction. Good. So far, so good. Now we have made an observation. We haven't explained anything yet. We can make one more observation or discuss one, and that's the decay of neutral kaons to a pair of muons. It turns out that those are not very likely. Even so, you would expect that the amplitude has a factor here of sine and cosine Cabibbo. So the amplitude should be in the order of sine theta Cabibbo times cosine theta Cabibbo. So when this was studied, the charm quark hasn't been discovered. And the explanation to why this decay is suppressed comes from the fact that there is a second diagram here, where we just replace the U quark in this loop with the C quark. This diagram contributes with a minus sign to the amplitude. And therefore, those two diagrams, they cancel, right? They are the same magnitude, about the same magnitude, and they have an opposite sign. So this was the first indication that there must be a force quark contributing to this kind of processes, the charm quark. When we now try to understand what's going on here, why is the W coupling modified, or why it's not the full down quark or a strange quark participating in the weak interaction, we can do the following here. We can rewrite, or we note that the weak interaction eigenstate, the eigenstate which participates in the weak interaction eigenstate, is not the eigenstate of the particle itself, the so-called mass eigenstate. So we have to write the weak eigenstate as a linear combination of the mass eigenstate, or vice versa. This can be done in this matrix form here, where we simply multiply the weak eigenstates with a matrix and just basically rotate it into the mass eigenstate. So this was proposed by Cabibbo and rather successful. But it didn't incorporate the third generation particles. And this was done by Kobayashi and Mascava, who generalized this scheme and proposed the so-called CKM matrix. C is here for Cabibbo, Kobayashi, and Mascava. Because of constraints we'll discuss in one of the recitations, this matrix can be parameterized or has only 3 independent angles and 1 complex phase as independent parameters. So you can choose different parameterization to capture that there's only 4 parameters in this matrix, which has 9 components. One is by thinking about this matrix as 3 independent rotations on this complex phase here. In terms of numerical values, you see that the diagonal elements of this matrix are very close to 1, meaning that this mixing is in the quark sector is a rather small effect. You find that those nearest off-diagonal elements are the order of 20%, and the next to next off elements are even smaller. Okay, this leads us then to the discussion that we can use different parameterization in order to capture those effects. We already discussed the standard parameterization, which you can really think about 3 different rotations, and the values of this of those angles are given here, together with the value of this additional phase. Another way to look at this is the so-called Wolfenstein parameterization, and this captures the fact that it seems like that there is a correction being applied to the actual particle. So you find elements in the order of lambda. Lambda is about 22%. Then you find elements which are in the order of 1 minus the lambda square correction. And then there's elements which are of lambda square and lambda third power. So this captures the matrix, and then there's higher order corrections to that, which are of order lambda to the 4th power. Okay. Because there's constraints on this matrix, and specifically unitarity constraints, meaning that we have 3 generations. If I make a mixing of those 3 mass eigenstate to a weak eigenstate, then unitarity, the total number of particles in this discussion is conserved. This will change if there would be, for example, a 4th generation particle. So the study of weak charge interaction with quarks helps us to understand whether or not there might be a 4th generation. We'll not go into too much detail here, but it also, the complex space explains part of our understanding of the p violation. And we might discuss it in a little bit of a later lecture. But nevertheless, so what we can actually form here is those unitarity constraints, just simply summing over the matrix elements, the scalar product of matrix elements, and those where the contribution vanishes. So those where J and K are not equal, those can be represented as a triangle. That's quite interesting. You can just rewrite this. You just say, so those 3 elements of the sum are equal to 0. Then you normalize by 1 element, in this case here, normalized by VCD, VCB. And so then this makes this point being 0. And so we have this nice triangle here, which has 3 angles, alpha, beta, and gamma, and this point here, rho and eta. And so this is a nice way to illustrate actual measurements of the elements of this CKM matrix, element. And without actually explaining how we do this experiment, you can assume that all measurements have, or you can understand that all measurements have to do with the weak interaction with quarks. That's how we have access to the CKM matrix elements. Sometimes this results in modification of masses or splitting of mass states, and sometimes it's a direct measurement of a coupling. When you put all of those measurements back together, you can look at this. So we see our triangle here. We see this point, eta and rho, which is given here in this eta and rho plane. And you see various number of measurements which correspond to elements of the CKM matrix.